Hi, this is Shahadad Hussain. Today I will discuss about complexity of an algorithm. The complexity of an algorithm computes the amount of time and space required by an algorithm for an input of size n. There are two types of complexity, space complexity and time complexity. In this video I will cover all about time complexity. So let's start. What is space complexity? Space complexity is the prediction of how much memory space is required for the successful execution of the algorithm. Time complexity is the total amount of time required by an algorithm to execute. Why is time complexity important? Time complexity allows us to compare algorithms and choose the most efficient one. Suppose we have a problem which can be solved in two different ways, algorithm A and algorithm B. Here we can see algorithm A takes less time than algorithm B to finish its process. That means algorithm A is efficient than algorithm B. So we will use algorithm A to solve our problem. In order to determine the best algorithm for a given task, it is important to analyze time complexity. Measurement of time complexity of an algorithm. To measure time complexity, there are three notations. Big omega notation, which is best case complexity, big theta notation, which is average case complexity, and big O notation, which is worst case complexity. What is best case complexity? Suppose we have an array and we need to find the value 5 by using linear search. In linear search, we check each of the elements of the array from index 0 until we find our desired item. At the beginning of the search, we could get our desired item. This is the best case complexity. Now, what is average case complexity? Suppose we want to find the item 9. It could happen that we keep searching and at the middle of the search, we get our item. This is called average case complexity. What is worst case complexity? Suppose we want to find the item 2. It could happen that the item is located at the end of the array. So, we need to search from index 0 to the last index of the array. This is the worst case complexity. Most of the time, we analyze worst case complexity for larger value of n. So, in this video, I will cover all about worst case complexity. General rules for big O. There are few rules for big O complexity. No worries if you can't understand the rules now. We will discuss these rules with example later. The first rule is drop constant rule. If our time complexity is O of 5n, then we will drop the constant 5 and write O of n only. The second rule is drop the non-dominant terms. Here's an time complexity order growth. O of 1 is the lower order terms, then O of log n, then O of n, then O of n log n, then O of n square, then O of 2 to the power n, then O of n factorial. Suppose we have a time complexity O of n square plus n. Here n is lower order terms and O of n square is higher order terms. So according to our rules, we will ignore lower order terms and write O of n square only. Now a question may pops into your mind that why we drop constant and lower order terms. This is because when the problem size gets sufficiently large, constant and lower order terms don't matter. Third rule is different inputs, different variables. Suppose we have an input A equal 20 and B equal 500. So A and B both are different. So instead of writing O n square, we will write O of A into B. Constant time complexity O of 1. An algorithm has constant time complexity if it takes the same time regardless of the number of inputs. Here is an example. This program print hello world. It will require only one operation to print the hello world. No matter what the value of n, it will only require one operation. Here n is constant. So this is O of 1. Here another example. This program will return sum of n plus n. No matter what is the value of n, this program will need only one operation. So here n is constant. So the time complexity of this program is of 1. What if this program returned n plus n plus n plus n? Still it required only one operation, so of 1. What if the value of n is million? Still this program required only one operation, again of 1. O of 1 is the most efficient big O. Another example of constant time complexity of 1, accessing an element in an array by its index. Here is an array named myArray and it has 9 items from index 0 to index 8. What if we want to find the value of index 0? We simply write myArray of 0 and we will get 15. What if we want to find the value of index 4? We simply write myArray 4 and we will get 80,000, the value of index 4. What if we want to find the value of index 8? Simply we write myArray of 8 and we will get the value of index 8, which is 12. No matter how large the array, the time to access an element remains the same, as we don't need to check each of the item one by one. We simply call the index and we will get the value. So here n is constant. If n equal 500, that means the array length is 500. Still, if we want to find the value of index 400, the time to access this element remains the same. We don't need to check one by one. So this is also of 1 complexity. Here also n is constant. Another example of constant time complexity of 1, adding or deleting elements at the end of a vector. Here is a vector named myVec, which has 6 items from index 0 to index 5. Suppose we want to add item 18 at the end of this vector. We simply write myVec.pushBack18. At the end of vector, new value 18 added. What if we want to delete the last item from this vector? We simply write myVec.popBack and it will delete the last item. Here we don't need to touch or change the rest of items index except last one. The index from 0 to 5 still remain the same. We only change the index of last item. So the operation will only once. So this is also constant time complexity of 1. No matter what the value of n, it will require only one operation to add or delete an item. Linear time complexity of n. An algorithm has linear complexity if the time taken increases linearly with the increase in the number of inputs n. Here's an example of linear time complexity of n. This program will print the numbers 0 to 89. Here the for loop will run till I less than 90. That means this program will print number 0 to 89. 0, 1, 2, 3, 4. What if n equal 10,000? If n equal 10,000, then this program will run till I equal 0 to I less than 10,000. That means it will print 0, 1, 2, 3 to 9,999. So we can say the larger the number of input, the longer it will take to complete the looping. Here time proportional to input size. Time items. The runtime of this program depends on input size n. So we can say the complexity of this program is O of n. Here another example. Here's an arithmetic operation I into y equal 5 plus 15 into 20. We know that the complexity of this operation of 1. And another for loop which will run from x equals 0 to x less than n. So we can say the time complexity of this program is O of n. Here total time complexity equal O of 1 plus O of n equal of n. But why? Remember the rules, we need to drop lower order terms. Here of 1 is lower order and of n is higher order term. Here the for loop dominates the runtime. So as per the rules, we drop lower order terms. So the time complexity of this program will be of n. Another example of linear time complexity of n. Here's a for loop which will run from x equals 0 to x less than 20. So the complexity of this portion will be of n, and for this for loop the complexity will be of n for this of n. Here total time complexity equal of n plus of n plus of n is equal of 3n. We can write it of n, but why? Remember drop constant rule. Either one for loop or 1000 separated for loop, we will drop constant and use of n only. So the time complexity of this program will be of n. Another example of linear time complexity of n, linear search algorithm. Suppose we want to find the value 13. So k equal 13, find k. It checks each element in the input until a match is found or the end is reached. The value of index 0 is 14. Is it equal to k? No. Then the next index 21. Is it equal to 13? No. Is it equal to 13? No. Is it equal to 13? No. We will check each items until 13 found or the end is reached. So it's not equal to 13. Not. Here the value of index 8 is 13, which is equal to our search item. So we can say algorithms with of n time complexity have a running time proportional to the input size. If n equal 90, in worst case complexity, we need to do 90 operation to find any items. So we can say the time complexity of this algorithm is of n. Another example of linear time complexity of n, vector insert. Here's a vector named myvec which have 9 items, index 0 to index 8. Suppose we want to insert number 17 at the beginning of this vector. Here we will write myvec.insert myvec.begin 17, and 17 will be inserted here with index 0. If we insert an items, then we need to change the rest of the items index number. See, all the index number should change. It will be 1, 2, 3 and continue till 9. So we need to loop the whole array. If the array length is 20, then we need to run 20 operation. If the array length is 40, we need to run 40 operation. So we can say the complexity of this algorithm is of n, which is linear time complexity. Another example of linear time complexity of n, vector erase. We have a vector myvec. If we want to erase the first item from this vector, then we will write myvec.erase myvec.begin. It will erase the first item. If we erase an items, then we need to change the rest of the items index number. See, it's 1, 2, 3, 4, 5, 6, 7, 8. But as we know, the index number will start from 0. So it will be 0, it will 1, 2, 3 and it will be 7. So we need to loop the whole array again. If the vector size is 100, then we need to loop the array 100 times. That means here time complexity is proportional to n. So we can say this program time complexity is of n. Quadratic time complexity of n square. Algorithms with of n square time complexity have nested loops that iterate over the input. Here's an example of nested loop. Actually, this program will print the multiplication table 1 to 10. This is the output of this program. So here is an inner loop and here is an outer loop. We already know for each for loop the time complexity is of n. Here for each outer loop of x, there is an inner loop of y which will run y equal 1 to y equal 10. So when x equal 1, the inner loop will be run and it will print this value from 1 to 10. Again x plus plus, then x equal 2, the inner loop again run and print the output. Same, x equal 3, the inner loop again run. It will continue till x equal 10. So we can say for each of n there is another of n inside. We already know a simple for loop time complexity is of n. So the time complexity is of n into of n is equal of n square. The time grows linearly to the square of the number of input elements. If input n equal 10, then we need n square equal 100 operation to complete the process. Here another example of quadratic time complexity of n square. So this is a nested loop and this is a simple for loop. For inner loop we know time complexity of n, and for outer loop of n. For each outer loop there is an inner loop of n. So the time complexity will be of n square. And we already know simple for loop time complexity is of n. Here total time complexity is equal of n square plus of n. We can write it of n square. But why? Remember there is a rules to drop lower order terms. Here of n is lower order terms, of n square is higher order terms. Here the nested for loop of n square dominate the runtime. So as per the rules we drop lower order term of n. The time complexity will be of n square. Logarithmic time complexity O log n. An algorithm has logarithmic time complexity if the time it takes to run the algorithm is proportional to the logarithm of the input size n. Binary search algorithm is a good example of logarithmic time complexity O log n. Binary search algorithm only works on sorted array. So we have a sorted array and we need to find the item 17. The rules is cut the array half and check first half or second half and remove half. First of all, we need to find the middle index of this array. So the formula is middle equal lower index plus higher index minus lower index divided by 2. So mid equal 0 plus 7 minus 0 divided by 2 is equal 3. So our middle index is equal 3. Now we need to check three conditions. Is the value of middle index is equal our search item. Second condition, is our search item greater than middle index value. Third condition, is our search item less than middle index value. We will check these three conditions. If our search item is equal to middle index value, then we got our answer. If our search item greater than middle index value, then we need to remove the left items and check the rest of the items. If our search item less than middle index value, then we need to remove the right portion and check the left portion only. So in this array, our middle index is 3, which value is 14, and our search item is 17. So is 17 equal 14? No. Is 17 greater than 14? Yes. 17 is greater than 14. So we need to remove the left portion and check the right portion only. Again we need to find the middle of this array. So middle equal lower index value plus higher index value 7 minus lower index value 4 divided by 2 is equal 5. So index 5 is our middle index now and its value is 16. Again check, is 17 equal 16? No. Is 17 greater than 16? Yes, 17 greater than 16. So we need to remove the left portion and check the right portion only. Again we need to find the middle and check. So middle equal lower index value plus higher index value minus lower index value divided by 2. So now our middle index is 6. What is the value of 6? 17. Is our search item equal 17? So this is true. So we got our answer. In 3 steps we got our desired search item. The complexity of this algorithm is O log n. Log n, we know the base is 2, so log 2 base 8. 8 is the number of input, n equal 8. So with this time complexity analysis, we can say how many steps we required to find any item in a worst case complexity. Basically, it's saying 2 to the what power is 8. Log 2 base 8 is equal what power? We know 2 to the power 3 equal 8. So log 2 base 8 is equal 3 steps. We can calculate this by using logarithm formula. The formula is log a base b is equal c, then a to the power c is equal b. Here log 2 base 8 is equal c, then 2 to the power c equal 8 according to this formula. Then 2 to the power c equal, we can write 2 to the power 3 as 2 to the power 3 is equal 8. 2 to cancel, c equal 3. So we only need 3 steps. What if large number n equal 33,554,432? How many steps need? Let's calculate this. Log 2 base 33,554,432 equals c. Then 2 to the power c equal 33,554,432. We can write it as 2 to the power c equal 2 to the power 25. So 2 to the power 25 is equal this. If we cancel 2 from the both sides, then c equal 25. So we only need 25 steps in a worst case complexity to find any item from this long array. In each step, the problem size is half, leading to a logarithmic time complexity. From the example you can see, in first steps we halved our problem size, then again in second steps we halved our problem size, in third stage we halved our problem size. So in each step the problem size is halved, leading to a logarithmic time complexity O log n. Linearithmic time complexity O of n log n. Algorithms with O of n log n time complexity divide the problem into sub-problems, each solved in O log n time. Merge sort algorithm is a good example of linearithmic time complexity of n log n. Here is an example of merge sort algorithm. The process is divide the problem into multiple small problems. So we divided the problem into multiple small problems. Then break down the problems into atomic sub-problems where they are actually solved, resulting in O log n. So here we break down the problems and solve them. The merging operation requires linear time complexity of n. Combining both logarithmic and linear factors, the overall time complexity is O of n log n. It recursively splits the input, sorts each half and merges them, resulting in linearithmic time complexity. Exponential time complexity of 2 to the power n. Exponential time complexity happens when the growth rate doubles with each addition to the input n, often iterating through all subset of the input elements. Anytime an input unit increases by 1, the number of operations executed is doubled. Example is recursive Fibonacci sequence. Here is a code of recursive Fibonacci sequence. This could calculate the nth Fibonacci number recursively. Here n equals 7. So we need to find the Fibonacci number of position 7. The Fibonacci function makes two recursive calls, Fibonacci n-1 and Fibonacci n-2. As a result, the number of recursive calls double with each increment in n. The time complexity grows exponentially with n, resulting in O of 2 to the power n different terms for inputs. Suppose A equal 100, B equal 200. There are two for loops in this program. The first for loop will continue till I less than equal 100. The second for loop will continue till j less than equal 200. So the time complexity for first loop will be of A, for second loop of B. So total time complexity will be of A plus of B is equal of A plus B. We cannot say O of n since A and B different. Another example, here is a nested for loop. The inner for loop time complexity is O of B, the outer for loop time complexity is O of A. So the total time complexity is O of A into O of B is equal of A into B. We can't say O of n square since A and B different. Big O time complexity graph. From this graph, we can easily understand which big O complexity is good and which is bad. Big O complexity of 1 is excellent, of log n is good, of n is fair, of n log n is bad, of n square and of 2 to the power n of n factorial, those are horrible. Suppose input n equal 10. Let's calculate which big O complexity requires how many operations to complete the process. O of 1 complexity required only one operation because here n is constant. O of log n require 3 operations. How we can calculate? We already know this. We can write 2 to the power c equal 2 to the power 3.3 something. C equal 3.3. We can write the integer value 3. For O of n, we only require 10 operation. For O of n log n, we require 3.3 for log n and 10 for n. So 33. For O of n square, we need 100 operation. How? N equal 10. So 10 square equal 100. For O of 2 to the power n, 2 to the power 10. So we need 1024 operation to complete the process. I hope you understand the difference between each big O complexity. Choosing the right algorithm. Analyzing time complexity helps us select the most efficient algorithm for a given problem. For smaller input size, even algorithm with higher time complexities may perform well. However, as the input size increases, choosing algorithms with lower time complexities become crucial. If you think this video is helpful, then please do like and comment. Don't forget to subscribe my channel. Thank you.